Everyone? Okay, we get started. Just let's see that it's recorded. It's recording. Yeah, okay. So, last time we were doing equivalence classes. So I'll post like homework 2 today or tomorrow.
Wait, what?
It's due on September 20th. But it's going to be something like 12 exercises that you'll have to do.
But we already have homework that is due next week. Do those two overlap?
Pardon me?
We already have one that is due next week. But
You have one that is due on 20. This one's due on 27.
No, this one says it's due on
13, sorry. This one is due on 13, next Friday. I will post one that is due in 2 Fridays. Where's the problem?
So those homeworks will overlap, and coming from now, they will always overlap by a week?
No, I mean, every week you'll have homework due. Does it matter when I release it? I mean, if I release it, everybody, does it matter when I release it?
I mean, the time that we have for it, yes.
Well, I mean...
So for the first 2 homeworks, we have 2 weeks each, and then after that, well...
Okay, so...
Naturally.
Yeah, I mean, now I posted it just because I am not allowed to have something due before I drop. That's it. Okay? I mean, I can postpone it next week, I can postpone it. I'll post it until next week. I mean, it doesn't... I don't think it should matter because it's written. If I post it now or I post it next week, it's going to be the same thing, as long as it's due the same day.
I'd rather it earlier so I can start.
Okay, so maybe I'll post it today. It's going to be something like 12 problems. I mean, I don't think you will be able to do all of them by the end of this lecture. Yeah, so maybe on Monday you'll be able to do them all. But you should be, guys, please, you should be able to do them. We should be able to do most of them. Yes.
I remember.
Guys, please.
Yeah. I remember last lecture, somebody mentioned something about the proof by induction question having like an error.
There's no error. There's no error. Okay. Great. Okay, last time we were talking about equivalence classes, equivalence relation. Recall that an equivalence relation on X must satisfy what are the 3 properties? Reflexivity. X is related to X for all X in X. The second property is symmetry. If X is related to Y, then Y is related to X. 3. If X is related to Y and Y is related to Z, then X is related to Z. What is this property called, everyone? By the way, have we all started the first homework? Yeah, please start it. Okay? Yes, sir. Slightly bigger. Okay. I'll try. Thank you. Okay, so let's recall. What did we say about the equivalence classes? The equivalence class of X in X under R. What is it denoted by? We denote it by XR. This is just the set Y in X such that Y is related to X. Or equivalently, by the symmetric property, Y in X such that X is related to Y. We see that by symmetry if Y is related to X and X is related to Y and vice versa. Are we good? Great. Now let's prove some results about equivalence classes. Oops. Got an email. So let X be in X and Y be in X. Then 1, the equivalence class of X is is not empty. 2. If y belongs to the equivalence class of x, then the equivalence class of x is equal to the equivalence class of y. 3. Is empty. This is empty set. 4. Okay? Are we clear? Are we good here? Remember what the equivalence class is? So let us remember the equivalence relation we defined on Z last time. I say that two integers are related if their difference is divisible by 3. Remember, how many equivalence classes did we get last time? 3, right? Are we good here? We got 3z, 1 plus 3z, and 2 plus 3z. Do you remember this? Yeah. Now, these are the 3 equivalence classes. Now, did any of them intersect or not?
No.
If you take 2 distinct equivalence classes, do they intersect?
No.
You can have a look at your notes. We wrote them down. So what are the 3 equivalence classes? What is the equivalence class of 0? 0, 3, 6, 9, minus 3, minus 6, minus 9. It's all multiple of 3, right? Remember? The equivalence class of 1 is all the multiple of 3 plus 1. So you have 1, 4, 7, minus 2, minus 5. Does this set intersect with the first set, with the multiples of 3? No. No. Okay? Are we all following here? Yes. Okay. We will do an example to see that later on. Now, why is that true? Why is the equivalence of class of x not empty?
Because there is x in it.
X is in it, right? Everybody, are we good here? X belongs to x. Since x is related to x. So x is not empty. Great. Two. What do I need to show? I need to show that if y is related to x, then the equivalence class of x is equal to the equivalence class of y. I mean, maybe we can have a, well, maybe I can do an example later to show you how this works. Okay, maybe we can do an example actually here. Okay, let's do the column example. So you're Nathan and you're Damien, right? Okay, so let's say that two students are related if they're seated in the same row, if the same column. Okay? If they're sitting in the same column, then they're related. We saw last time this is an equivalence relation. Agreed? Okay, so the equivalence class of Nathan. Could you raise all your hands? Everyone that is related to Nathan. Nathan is sitting here, right where I am. Yeah, everybody raise your hands. Okay? Great. Now everybody, is Damien related to Nathan? Is he sitting in the same row as Nathan? Okay, everybody that is related to Nathan, please raise your hand. Nathan is sitting. Yeah, okay. You saw it, it's the same set of students that raised their hands. You see this or not? Yes. So, if y belongs to x, then the equivalence class of x is equal to the equivalence class of y. We see that? Okay, what is your name? Vala. Vala? Yeah. Okay, so everybody in the equivalence class of Invala, can you please raise your hand? Okay, now everybody in the equivalence class of Nathan, could you please raise your hand? Nathan, here. Did anyone raise their hand twice? That's the third property. They're equal or totally disjoint. Is it more clear? We'll do a more abstract example later on. Okay, now how do we prove this? So if let y belong to x, let y belong to the equivalence class of x, we need to show that the equivalence class of y is equal to the equivalence class of x. So what do I really need to show here? Yes? Yeah, but what do I need to show first? If I,
Sorry.
yeah, go ahead.
If any element is related to y, then x is related to the element.
Exactly. So we need to show, we need to show it in both ways, right? Y, the equivalence class of y is inside the equivalence class of x, and the equivalence class of x. Okay, let's show this one first. Did that example make it a bit clearer? Like, what is an equivalence class? Like, an element cannot belong to two equivalence classes, basically, to two distinct equivalence classes. That's it, basically. Okay, so let Z be in the equivalence class of Y. We need to show. This is the first one. So this is the. Okay, that doesn't. We first show this one. We need to show that Z belongs to X. Agree or not? Agree or not? That's what I need to show. Okay, so let Z belongs to Y, to the equivalence class of Y. Then Z is related to Y. Agree? Everybody agrees? Ben? Yeah? Yeah, no, you were saying?
We use the transitive relation.
Exactly. Now we know that Y belongs to, by assumption, Y belongs to X, to the equivalence class of X. So Y is related to X. Everybody agrees? We agree or not? Okay, so Z is related to Y and Y is related to X. What can I use to say that, to finish, that Z is related to X?
By transitivity, Z is related to X.
By transitivity of R. Z is related to X. Well, I have shown that any element in the equivalence class of Y belongs to the equivalence class of X. Hence, Y, the equivalence class of Y is contained. Are we good here? Everyone. This is one of the most important things in Algebra 1. Equivalence relations. Later on, we'll just be working with sets of equivalence classes. Okay, so please make sure you know this. Are we good here? Any question? Please do raise your hand if you have anything. Yes?
Is this good plus? How do you know that y belongs to x?
By assumption. If Y belongs to X.
Oh, okay.
Yeah. Then?
Oh, okay.
Okay. Any question? Okay, now how do I show that X is contained, that the equivalence class of X is contained in Y? Do we need a lot? Do we need to do the same thing, or just the same argument with X and Y flipped?
It's similar, but not exactly the same, because you know that Y is related to X, but you still have to say that X is then related to Y.
Exactly.
By symmetry.
By symmetry. Exactly. So technically it's the same argument, because Y and X are related, if X and Y are related. Okay? Are we good here or not? I mean, we can do the proof again, but I feel we should be able to spot that it's going to be the same argument. What we have shown that if A belongs to the equivalence class of B, then the equivalence class of A is contained in the equivalence class of B. Agree? Everyone?
Yes.
Yeah. Now, if Y belongs to the equivalence class of X, then X belongs to the equivalence class of Y. And so the same argument will work. Okay? Try to think about that. It's an important argument. It's by symmetry. Okay, no, I'll keep this one. Sorry about that. related to y, and y is related to x. The exercise, filling the details is an exercise. Okay? So 2 is proved. Now let's prove 3. 3, what does it say? It says that 2 equivalence classes are either totally disjoint, or they're equal. That's a pretty strong statement, right? Like 2 sets have no intersection at all, or are totally equal. How do you prove that? Yes? So, yeah, you? Yeah, no. Actually, yeah.
It's
Sure.
they aren't
Yeah, we could do that. Yeah, we could try that.
one, but then
Okay, yeah, that's good. That's good. Okay, yeah, we could do that. If x intersection y is empty, then we're good, right? Agree that we're good. If it's empty, then we're good. Now suppose it's not empty. I think you mean by cases, basically, right? If it's empty or if it's not empty. Yeah. Suppose it's not empty. If it's not empty, let Z and Z, let Z be in the intersection. Yep.
now you can show that they are the same.
Exactly. Very good. So if Z is in the intersection, then Z belongs to the equivalence class of X. Agreed? Everybody agrees. Now if Z belongs to the equivalence class of X, what does the second proposition tell me? It tells me that the equivalence class of X is equal to the equivalence class of Z, right? Right? Everyone. Similarly, the equivalence class of X, the equivalence class of Z will be equal to the equivalence class of Y. Because Z belongs to the equivalence class of Y as well, right? Let's write this down. Z belongs to the equivalence class of Y. So the equivalence class of Z. Are we good here? Yes?
The first part, like where you're saying the intersection is empty.
Yeah.
Would it be better to say like either one of them is empty, so then the intersection is empty? Because it seems like you just restated like what we're trying to prove in the first part.
What do you mean? The equivalence class is empty? Yeah.
So like when you started, you just
Yeah.
restated that exact thing. Is that like?
Yeah, I mean, so you have 2 cases, right? If it's empty, does this theorem follow?
Yeah, but it's like more specifically, would you say either one of those 2 sets is empty? So then.
Well,
the intersection is empty?
what do you mean the 2 sets? What 2 sets? X or Y?
Yeah.
No, because X is not empty, right?
Right. Okay.
Y is not empty. An equivalence class is never empty.
Okay.
So you can have 2 sets that are not empty that have an empty intersection. Okay? Okay, well, Z is equal to R, Y is equal to R. So Z is equal to X is equal to Y. Right? We're done. If the intersection is not empty, then this works. Are we good here? Okay. What time is it? 25 minutes, 30 minutes left. Are we good here? Everyone, any question on this? Yes?
At first you said if the equivalence class of x intersected with the equivalent class of y is empty, then we're good. What do you mean by then we're good?
The theorem is satisfied, right? If it's empty, then this theorem holds, right? Yeah. We're good is causing a problem. Then prop 3.
Then property holds.
Right? Okay.
And so we do else, suppose, and continue the proof.
Yeah, exactly. If it's empty, then you're good. Then the theorem is proved. And if it's not empty, then the theorem is proved. Right? So in all the cases, the theorem is satisfied. The conditions of the statement of the theorem is satisfied. Right? Are we good here? Yes? Oh. Any question? Please do ask questions about this. This thing is gonna follow us until the end of the course. Yes, Yusuf? Well, that's what, so if the equivalence class of x is not equal to the equivalence class of y, yeah, then the intersection will be empty, yeah, definitely. We proved that. Well, we proved that if the we proved the contrapositive, right? We proved that if the intersection is empty, if the intersection is not empty, then they must be equal. Okay? I mean, you know, if they're not equal and they intersect, right? That's it. Yes?
How would we go the other way?
I mean, you don't need to, right? If you have a simple way, why would you do that? Okay? Yeah?
How is the equivalence class of set introduced?
Could you please?
How is the equivalence class of set introduced?
Okay. So, if the intersection of the two equivalence classes is not empty, then you can find the z in the intersection. Agree? Now, if z is in intersection, then z belongs to the equivalence class of x. Now, if z belongs to the equivalence class of x by proposition 2, the equivalence class of x, of z, is equal to the equivalence class of x, right? Agree? Do the same argument with y. You get the equivalence class of z is equal to the equivalence class of y. But wait a minute, the equivalence class of x is equal to the equivalence class of z, and the equivalence class of y is equal to the equivalence class of z. So all of these three classes are equal. Now if you have two sets that are equal and you intersect them, what do you get? The same set. Okay? So please make sure this is understood, because this is very, very, very important. Okay? Great. Okay. Oh man, why did I erase that? Okay, let's do it well. Okay. Should I do an example of this to see how this works, or is clear how it works? Do you want an example? Let's do an example. Okay, then I'll leave something to you as an exercise. Example. Recall. Let x and y be in Z. Say that x is related to y, and x minus y is divisible by 3. Okay. Now, what are the equivalence classes? Last time we saw the equivalence classes. It is the equivalence class of 0. it's just the set x and z such that well, that doesn't, y minus, well, it doesn't matter, right? Does it really matter? Such that y, it doesn't matter, y minus x or x minus y. Okay. What is this? What is this set? We said that this is just minus 3, 0, 3, 6. These are all the multiples of y is divisible by 3 means it's the multiples of 3. How did we denote this set? 3 times z, right? You take all the integers and you multiply them by 3. Great. Now what is the equivalence class of 3? What is the equivalence class of 3? Everyone. Is it the same?
Yes.
So it's the set of x, well, it's the set of, it's the set of y and z such that y minus 3 is divisible by 3. It is the same thing as if I'm saying y is divisible by 3. Yeah? This is also equal to 0. Yes, sir.
Question of notation. How do we come up with the subscript? Like, can we just
3. Yeah, I came up with it. Okay. 0.
No, but for like problems we solve.
Yeah, I mean, you can use R.
But it's not forced to just be R.
No. Yes.
When it's explicit, do we put something there? Then we only have like one.
Yeah, I mean, for now we're gonna use that. I mean, later on in the course you will know it. Okay? It's gonna become a habit. Yes? Pardon me? Depends on how you define things, right? It's just a notation, right? I can call it, I don't know, I can just remove that, you mean? Yeah, sure. Okay, I mean, it's just a notation to say that this is the equivalence class in that relation. Okay? Any other question? You see, okay, now what's the equivalence class of 1? The equivalence class of 1, what is that? Is the set y and z such that y minus 1 is divisible by 3. What is this one? We wrote it last time. It's this set. If you add to it, if you add 1 to every single element, right? Remember? This is 1 plus 3z. Okay? You understand this notation? You take, are we good with the notation? Yes. You just take this element and you add 1 to every element in it. Now, the equivalence class of 4, is it the same or not? The equivalence class of 4, to what is it equal? The equivalence class of 0 or equivalence class of 1 or neither? 1. Equivalence class of 4. Okay, I mean, let me write this down. 1, 4, 7, and so on, and then you have minus 2. Okay. The equivalence class of 2. What is the equivalence class of 2? It's 2 plus 3z, right? Which we denoted by 2, 5, 8, and so on. Minus 1 here. Okay. Are we good here? Yes. The equivalence class of 8, to what class is it equal?
Equivalence class of 1. No, 2.
8.
2.
Everybody. Are we good here? Okay, great, awesome, this is good. As long as, when you see an 8 in the equivalence class of 2, automatically it becomes the case that the equivalence class of 8 is equal to the equivalence class of 2. Now here I have written 3 distinct equivalence classes. 3 distinct equivalence classes. This one, this one, and this one. Okay? Who can volunteer to give me an integer? Let's say Nathan, can you give an integer?
17.
5. Can you see 5 in one of these equivalence classes? Does it appear? Does 5 appear in here? Okay. Someone else, an integer.
7.
7. Can you see 7 in these integers?
Yes.
In these equivalence class? You see it here. Now notice that every element will appear in an equivalence class. And how many times will it appear? Once and only once. Okay? So if you take the unions of these three equivalence classes, what do you get?
All
The union, not the intersection.
integers.
Take the union of these three sets, what do you get?
Zero.
The entire set of integers, right?
Positive and negatives.
No, positive integer is contained. You can get the negative integer, right? Take -8 for example. Where is -8?
It's going to be in 1.
1. Exactly. Is it?
Yes.
-2? Yeah.
Yes.
Yeah. -9 plus 1. Okay. Now let us formalize this. And you have to prove this statement as an exercise. We know what a partition of a set is, or should I define that? Define? Okay. Let X be a set. And suppose what? Oh, by the way, sorry, I forgot to say something. How many equivalence classes we have here? 3. Can you give me a set of representative of each class? So the first class, 3z, can you give me a representative? 0. The class 1 plus 3z, could you give me a representative?
1.
The third class, 2 plus 3z, could you give me a representative? 2. Okay, so 0, 1, 2 are representatives of the classes, of the equivalence classes. Is this the only set of possible representatives or not?
No.
Can you give me another set of representative? Yeah, say
3, 4, 5.
3, 4, 5, right? 3 is here. 4 is here. 5 is here. Are we good here?
Yes.
Yes?
What do you mean by representative?
So an element that belongs to the equivalence class.
Oh.
That's it. Okay?
Distinct ones.
Distinct, of course. Yeah. I mean, yeah, you cannot have the same class.
Yeah.
Okay? Let X be a set.
Excuse me?
Yes.
Just, it's very small, but when you write, can you make a little more distinction between the big X and small X?
The big X and small x. Yes.
Yeah.
Okay. Yeah. Okay. I mean, you know,
No, the small x, don't you do it a little curly though?
I do it curly,
You
but
could like
sometimes
underline
there's going to
it.
be a problem. Now, hopefully,
Sometimes you forget to do
the
it.
S is going to be a problem for me, especially when I write it this way. Everybody confuses it with F5. But let's hope I won't write many S's, because we're going to write many 5s, I think. Let X be a set. A partition of X is a collection of subsets xi of X such that xi is not empty for all I. 2 xi intersection xj is empty if I is different than j. And 3 x is the union of the x's. Okay? Basically, I have this equivalence relation. Okay? I have these 3 equivalence classes. Do they form a partition of Z? Let's see. Look at these 3 equivalence classes. Are they empty? Are they empty? No. If 2 of them are different, do they intersect? Do they have any intersection? If they're different, do they have any intersection? Take the intersection of 2 distinct equivalence classes. Is it empty or not? Okay. Now, what is the union of these 3 equivalence classes? Is it the entire integers? Yeah. So equivalence classes form a partition of the sets. Okay? Let me write down, well, I'll erase this one. Theorem. There are two ways, there are two parts of the theorem. Let R be an equivalence relation on X. Let R be an equivalence relation on X. Let R be an equivalence relation on X. Then the equivalence class of R partition X. Okay, that you can prove this theorem, right? Can you prove this theorem? Can I leave it as an exercise?
We'll try.
Okay, try it. This theorem is easy. It's easy. Okay, it's not that bad. Just follow the same steps. Okay? Yeah? Okay, let's you can write X is union I in I, Xi, where Xi is a set, for example, S and phi here of representative of the equivalence classes. Two. Let Xi say let Xi be a partition of X. Okay? I mean, suppose that you have finite. Suppose that it's a finite partition. You have finitely many sets. I mean, it's not true in general, but that's okay. Let Xi be a partition of X. Then there exists an equivalence relation on X whose equivalence classes are the X's. Let's do an example. So I mean, let's take A to be a set 1, 2, 3, 4. What's a partition of this set? You can write it as 1 union 2 union 3, 4. Right? Now the claim is that you can find an equivalence relation on A such that these are exactly the equivalence classes. Also, this is left as an exercise. I mean, let me give you a hint. Hint. Say X is related to Y if XY belong to XM. Okay? Then prove it. Okay. Great. It's left as an exercise. Maybe I can add it to the second homework. It's not, but I mean, again, it's not bad. Okay? Yes?
I'm sorry, I'm kind of, I don't know if you mentioned this, but like, what does I, like,
I is the index set. So, yeah, have you seen index set? No. Okay. Analysis. So I mean, you know. Just it's the set of all partitions. It's the set. It's 1. X1 is 1.
Okay.
X2 is 2.
Oh, okay.
X3
okay,
is
okay.
3, 4. Okay.
Okay, got it.
For example. Yeah.
Wait. I forgot my question, sorry.
Okay. Great. Yeah, this theorem, I don't want to state it because I have to. I is just an index set. Okay, where I is an index set. Okay. It's just a way to label the x's basically. You have one way to label them as 1, 2, 3. So assume I is finite. Basically, you have x1, x2, x3 up to xn. Okay, that's not a problem. Okay, great. Now let's start with a new chapter. Integers. Now in your analysis courses, I think you have, or any discrete math courses, you have proved that you have proved something on induction, right? Or not yet? You have proved that induction has 3 different forms and they're all equivalent or something like that, or not yet?
We have seen what induction can be, but not all.
Okay, so here we'll not prove them, I'll just state them. The proofs are in the book, or not. But this course is not about induction. This course is about groups and rings. Now it's fourth lecture, and we did not get to groups and rings. So yet now we're doing the preliminaries, but I won't go into details of proving what induction, or what are the equivalent principles to the principle of mathematical induction. Okay, so let's talk about integers and induction. Now there is a principle that we're going to assume, which is called the well-ordering principle. The well-ordering principle. What does it state? Let S be a subset of N that is not empty. Then S has a minimal element. This is an axiom that you will assume. Okay? Now, there is a principle, the first principle of mathematical induction. Let S be a subset of N. Such that 1 belongs to S and 2. If N belongs to S, then N plus 1 belongs to S. Yes?
Sorry, what does that word say before element in your definition of well-ordering principle?
Minimal. Minimal. Least, minimal, anything you want. So let S be a subset of N such that 1 belongs to S, and if N belongs to S, then N plus 1 belongs to S. What can I say about this set? Then S is equal to N. Okay, let us see why this is true. Let us give I mean, suppose you have a series of dominoes, right? Okay, you have dominoes on the table. You know something, that if one falls, then the next one will fall, right? if you space them close enough. If one falls, then the next one will fall. Agree or not? Yeah, everybody? Now if I tell you that the first domino will fall, I will push the first domino. Will the second one fall? Will the one after the third one, will it fall?
Most likely.
The fourth one?
Most likely.
Fifth one? All of them will fall. Right? This is the principle of mathematical induction. So all the dominoes will be falling. Because the first one falls, and if one falls, then the one after will fall. Okay? This is the principle of mathematical induction. Maybe I can prove, how much time do I have left? 2 minutes. We can prove that the first, statement
No, so you
implies
literally have 2 minutes. Are you sure you can do it?
Yeah. Okay.
Is it a one-liner or not?
We'll see. Okay. Now, suppose the well-ordering principle. Well-ordering principle implies the first principle of mathematical induction. So how do you do that? You can do this by contradiction. So suppose that S is a subset of N with with the following properties. 1 belongs to S, and if N belongs to S, then N plus 1 belongs to S.
What does FPMI?
I claim that S is equal to N. Yes.
What does FPMI mean?
Pardon me?
FPMI.
FPMI, first principle of mathematical induction. Okay? I mean, it's a quick proof. So suppose S is not, suppose S is different than N. Then S complement is not empty. Okay? If S complement is not empty, by the well-ordering principle, S complement has a minimal element. Has a least element that we'll call M in N. Now I will get to a contradiction. Does N minus 1 belong to S? Does N minus 1 belong to S bar or not? No. Does not belong to S bar, since M is the least element of S bar. Now if M minus 1 doesn't belong to S bar, where does M minus 1 belong to? So M minus 1 belongs to S. Agreed? Now this set, S has the property that if N belongs to S, then N plus 1 belongs to S. M minus 1 belongs to S, then M minus 1 plus 1 is equal to M belongs to S. So M belongs to S bar and S at the same time. That's a contradiction. Contradiction. Okay?
What is the S bar
Part has a least element. Okay, so it was a quick proof. Again, I don't want to, I mean, these proofs I don't think I will examine on, because this is not the point of the course, okay? So, okay, great. See you. S bar is the complement of S.